Okay, welcome Genevieve and Tandon and Michaela and Kimberly. This is the week 10 webinar. We're almost done actually. This is the penultimate webinar because next week there is no webinar. Do you know why? Yeah, we have a holiday. We have Thanksgiving week and the whole week is a holiday at our college. So everything is off. I'll be grading, but there's no assignments, there's nothing to do, there's no posts, there's pretty much, you're just off for the week, okay? I mean, you're welcome to do work if you want to, but there's nothing required, there's nothing assigned. So that's just a big note is that we take a week off next week for Thanksgiving, and then we come back again the week after, and that'll be our last webinar because the week after that's the final. So that's just a big note is that the course is coming to an end pretty soon. So this is, again, it's the last full webinar of a full section, okay? After, you have a lot of cooking to do. That's good too. I have some cooking tonight for dinner. This is the last full webinar of a full section, of a full chapter, because in week 11, I do a short little piece on chapter 13, but I've cut most of chapter 13, and then I spent a lot of time reviewing for the final. Just a note about some things that are coming up. So what's the big thing that is due on Sunday? Yeah, project 2. Take it seriously. It's a big part of your grade. And by Wednesday, which is only 2 days from now, you need to submit your draft if you want me to look at it. And I'm telling you, if you don't submit it to me and I don't look at it, you're not going to see all the mistakes you made. So it makes a big difference, okay? So I like to call it Wednesday night, not Thursday night. So your goal is Wednesday late night. So that's when you want to have it. And first come, first serve basis as always. So if you submit at the last minute, then it may be a while before I can get it back to you. So again, and you don't have that many days. So if you send it to me Tuesday, then there'll be no issues. There's no, see, I really purposely don't have a limitation on pages because if I did, then everyone plays the game and has extra space and all that kind of stuff. More important is you have all the content you need. This project often is fewer pages just because you don't have any graphs to draw. So if there's no graphs, then the graphs take a lot of space. So sometimes the pages is a little bit less just because there's no graphs. It's pretty much all writing. Okay, the only thing that isn't writing is the copy and paste of your statistics from the spreadsheet. Okay, and that's required, by the way. You lose a whole grade if you don't do that. Okay, yeah, same spreadsheet, but you're going to use the second tab instead of the first tab. Okay, so same spreadsheet. So if you have that spreadsheet, if you've already made a copy of it, then you've got it. Okay, you don't have to do anything. You just open it up. So that's the good news, is that you only have to have the one copy. Okay, are there any questions? Let me pop up the things to do today. And today's like I said, it's an important week.
I have a question. It's Kimberly. So just a point of clarification for the project, because as I started the intro today, and then I was looking at data.
Mm-hmm.
So for the hypotheses that we chose, there were a lot of articles when I was researching where they've done analysis already, but you don't want us to utilize that, correct?
Right, your job is to do the analysis, not to read someone else's analysis.
Gotcha, okay.
So if the analysis is already there, then it's not a project.
Gotcha.
You see? You're supposed to be collecting your own data and do an analysis of that data, okay? And the collection could be online of the data, but you're not supposed to just write about someone else's project.
Okay.
Does that make sense?
Yes. I was considering going to like the CDC and seeing if they just had data available.
Yeah, data is fine. You can grab someone else's data, but but don't go to an article where they've already done the hypothesis test and have the data and then grab that data because they've already done the hypothesis test. Does that make sense?
Gotcha.
Yeah, and if you are grabbing data, you have to put that in the bibliography of where you found it.
Okay.
you know, because it is a paper, and paper, if you ever use someone else's material, that's just it's actually a legal requirement. You always have to write down that you got it from this group or whatever. Does that make sense?
Yes.
Whereas if you're doing a survey, then you state that you did the survey. Do you see?
Okay.
But collecting data from the internet is much easier than doing a survey. You know, not that you're not allowed to do a survey, but, you know, less time consuming.
Right. Okay. Thank you.
Okay. Other questions? A good question, though. Really good question. That could be about anything. Okay. Okay. I just want to note in terms of the discussion post this week, make sure that you can answer the discussion post to all the questions on the discussion post, which is basically table of contents today, because that's what the discussion post is about, the reply to it. If you can't do 2, 3, 4, 5, 6, and 7 from the discussion posts that you post, then it doesn't work. Okay, so you have to make sure that you can do that from the discussion post. Okay, so because there's a lot of partial regression stuff that you'll find, and it doesn't give enough information, like to find the y-intercept, things like that, and then it won't work. So that's just a note for the discussion post assignment. Okay, other questions? Other questions? Okay, my other recommendation for the project is read this project discussion board and see what other people have done and see my comments to see what works and what doesn't work. And that helps you figuring out what you need to do for yourselves, especially if you don't have something figured out yet. And at this point, hopefully you all have something figured out yet, but I've noticed that not everyone does in terms of, I haven't seen it at least on the posts. So make sure, you know, read through and see what other people have done and what worked, what didn't work. So it has to be a chapter 10 quantitative question. So that's important. Okay, it's not chi-squared. Okay, if there's no more questions, I'm going to get to something that is, I consider, the most important thing. And like I said, I don't know all of you. You know, in fact, I don't think I don't think I know any of you personally. So I don't know. Is anyone from Tahoe? I know I have a lot of people from all over the world, but my guess is I might have some Tahoe people. Any of you from Tahoe? Okay. All right. So we got one person from Tahoe. Carson, pretty close. Close enough that you can understand this. All right. So since you said you are, what is the most important data collection that happens? There's 3 of you that are close enough. What is the most important data collection of all from our area? Snow precip actually is not the most important. Okay, there's not that much money that's given by the government, for example, in snow precip. Tourist data, fire, tourism, no. Yeah, the hint is literally hundreds of millions of dollars have gone in from the government for this, to make this, to look at this and to fix the issue. Not the roads. Keys, no. All right, maybe I should show you. I thought, wow, usually I ask and everyone gets it. Good, the lake, okay? And in particularly, what about the lake? Not how pretty it is, you know. Yeah, the clarity, okay? So if you're not from Tahoe, that's okay. Again, you're not required. Did I already do this already? I better check. Yeah, good. Just want to make sure I did hit record, because this is the only one today, and it does say pause and stop. Good. Let me double check. I get all nervous. Did you hear this meeting will be recorded? Oh, good. Just want to make sure that it is recording. Okay. It's hard when I'm sharing my screen to actually see that it's recording. It doesn't show me. Okay, so that is the most important thing in terms of our area, in terms of data collection. Okay, and there's others. There's other data collection things. Okay, so if you're not from Tahoe, and if you don't even know about Tahoe, what we're famous for is our lake. Okay, that's the biggie. Again, we have good skiing, we have gambling, but there's a lot of places with that. But we have a really special lake, and what's special about it is it's really blue and really clear. Okay. And what we don't want to have happen is for it to lose its clarity. Does that make sense? So let me give you a little historical piece. I was actually here. So I'm old enough that I can talk history, which is scary. Um, I hadn't been teaching that long, but a while. And the most important person in the country came to Tahoe. So who's the most important person in the country? Anytime? And maybe you, but yeah, the president. Okay. Whether you like the president or not, the president is the most important person. And the president came to Tahoe and came to an environmental dinner, basically. And one of the cool things is my statistics student was there with him. Okay. It was President Clinton. It was a long time ago. My statistics student was there with him, serving him lunch, because my statistics student worked in the restaurant. And she actually told me that what happened, which was really cool. And what happened is that the UC Davis scientists are in charge of looking at the data from our lake. And they showed our president the data from the lake. Okay. And fortunately at the time, so Clinton, he actually did understand statistics, which I can't say about every president that we've had. We have not had presidents. We've had presidents that definitely don't understand mathematics and science very well, but Clinton did. And let me show you what he was shown. And of course, I'm going to show you more than that because when I go to the Davis website, it shows me up to today, but we'll pretend it was 20 years ago. So around the year 2000. And what they showed was this. Okay, they made it all pretty because when you're given a presentation of the president of the United States, you make it pretty, and I would be so nervous if I had to do that. Uh-oh, what just happened? Okay, there it is. Okay, and this is what they showed. And I'm not sure, those of you who live in Tahoe, what happens is this is the UC Davis boat, and they drop what's called a siki dish, which is just a fancy word for a small white plate. And they put it on a string and they kind of let it go slowly down in the lake until they can't see it. And as soon as they can't see it, then they measure the amount of string that came down and they call that the lake clarity. Okay. And they make sure that it's somewhat cloudy so that there's no reflections that are causing issues and all that. And it's not windy. So that's what they do. And I actually talked to the Davis researchers and had a really neat conversation. I smiled so much because I asked him a question and I asked him, well, when you do this, because I've heard that you actually do more than one sample each year. And I asked him how many did they do this year to come up with the lake clarity for the year? Any guess? The hint is I smiled a lot. Not 12. That wouldn't make me smile at all. That would make me frown, cry maybe. Not 500. That's way too much energy because that's more than once a day even. Yeah, there it is, 31. Okay. And hopefully you're all smiling too because you know the significance of that number. It's over 30. From then on, I've always used over 30. I had kind of before, I'd waver. And then on, when I heard from the UC Davis researchers, now I just use over 30. So 31. So every year, what they do is they take 31 different measurements throughout the year. And that way, if there's over 30, what can they assume? Or what can they conclude about the sampling distribution each year? In one word. Yeah, it's normal. So again, it's very important. We've done this a lot that you all get that the sampling distribution is normal if you have over 30, and that means you can do all kinds of good research. Okay, so again, I'm always happy when they do it right. And as I've mentioned, I've done a lot of consulting work for different scientific groups like the Forest Service and universities and stuff like that. And the biggest disaster is when they have too small sample size. But the fact that UC Davis had the right sample size, I was so happy. I didn't have to give them any criticism. Okay, but they've actually done a study. They did what's called a meta study, which is a study of studies. And they found out that more than half of the published papers make some error in statistics. It's kind of sad. So they're not statisticians. There's people who are in something else like psychology or chemistry or something, and they've maybe taken a stats class and they're not perfect. So the hope is that you're not going to be perfect, I'm sure, but the hope is that you'll at least know that the sample size needs to be over 30 for quantitative data. And this is definitely quantitative because they're measuring how deep it goes. Okay, so the way they drew this with all these Seeky disk dots is called a scatter plot. So a scatter plot is the graph of this kind of data. And what makes this data special for this week is for each dish, there's two numbers. There's the X coordinate and the Y coordinate. So for example, this dish right here has its X coordinate as 80 and its Y coordinate as 25. Do you see that? Any questions on that? Okay, so this week is all about when you have two different quantitative data, two different quantitative variables, but their variables usually are not something that you're going to be subtracting. Like in chapter 10, we looked for the difference between the means. Do you remember that? When we had two quantitative variables. Any guess on why you would not do that here? You would absolutely not do that? Why it's just nonsense? See y'all jumping in. Give you a moment. As soon as you see it, then you'll know that it's nonsense. All right, I don't see y'all jumping in, so maybe I'll tell you. So if you look at this point, this is 80, 25. Does it make any sense to do 80 minus 25 and say that's what, 55? Because that'd be the difference between the two numbers, right? What's the problem with that? Any thoughts? It's not about accuracy. The word is nonsense. No, it's not about shouldn't change. It doesn't tell us anything. To say 1980 minus 25 meters and subtract and you say 55 what? It's silly. Does that make sense? It's just nonsense. You can't even talk about it. You can't take the year minus the number of meters that you look down. They don't even have the same unit, so you can't subtract those two things. So that's one thing I want to make sure that everyone gets, when you're going to be using the chapter 10 stuff and when you're going to use chapter 12 stuff. And now we're in chapter 12, by the way. And we're going to use chapter 12 when we have two quantitative variables and we're not comparing the variables. What we want to see is that as the value of X increases, is there a tendency for the value of Y to increase or decrease, or maybe it's just there's no special tendency at all. And in particular, does it increase or decrease in a linear fashion? So is there a line that goes through these values? Any questions so far on that? So that's what that's all about, is the scatter plot helps us understand what's called the regression line. Is that clear? Okay, we could even draw that line And we're gonna pretend that we're President Clinton's group, which means that we're gonna stop around here. And can you all eyeball a line that is not through every point, but actually kind of approximates the points pretty well? Can you eyeball a line? Is that a yes or no? Yeah. Yeah, I can eyeball a line pretty well. Okay, and in fact, I think I can draw one. I think you can see it if I draw. So I can draw a line. Can y'all see that line? Okay, good, good. So that's a line that I can draw. And that line is not the line of all the points because these points are not linear. And in fact, if you look from say 1983 to 1987, it actually goes down. Do you see that in this little spot? So this goes up and down, but there's more up than down. Any questions on looking at this? Okay, I will let you know that there's a lot of mathematics behind it, and you're probably used to this class. How much of the mathematics itself do you think you're responsible for? Like to come up with this line? Yeah, none of it. Okay, the mathematics is pretty intense, and I'm not going to do that with you guys. If you decide to take my linear algebra class, okay, maybe even third quarter calculus class, then you'll get it, but not in our class. Okay, you need some advanced math. But you can trust me that you can actually come up with this equation instead of just eyeballing it. There's actually an equation. Okay. All right, now ready for a trick question? So when you're looking at a line, there's a slope and a y-intercept. Is that clear? That's not the trick question, by the way. That's supposed to be clear. Okay. Isn't it the means of both the x, the y, and the x? I'm not sure if by the means of. It's a line. We're just looking at the line. And a line's not a number. It's a line or an equation. So mean point, I'm not even sure what you mean by that either. For the line. So we have a line, but it's not a point, it's a line. Does that make sense? Okay, so there's just a line, and the line is a good fit for the points, at least eyeballing it. And well, I can tell you that later and kind of talk about what fit means, but that's later in our day. All right, so now what we see is we have this line. And when you have a line, what two numbers in your basic algebra do you learn that characterize a line? What two important numbers when you think about a line? Not x and y. Those are coordinates, and there's lots of numbers on the line. Not beginning and end. Lines don't begin or end, actually. They go forever, even though I only drew part of it. When I say it, you'll all say, oh, yeah, of course. Hopefully, you know. Interval, no. A and B. B is one of them that most people know. Kind of. A and B is what we use in statistics, actually, but that's not what you learn in algebra. So I want words. Words are better. Still not seeing it? All right, let me tell you, but I think you all know. Slope and y-intercept. Now, don't tell me you've never heard those before. That when you think of a line, there's a slope and a y-intercept. Any questions on that? So I'm assuming you all know those things. Okay, so the slope is a rise or a run. So in this case, it goes from about 30 to about, okay, so notice, by the way, is the slope positive or is the slope negative? Trick question. All right, so I told you it was a trick question. Okay, and this is UC Davis. Okay, now there can only be one. You can't have positive and negative for a slope of a line if you just have a line. Okay, but it's a trick question. Now, if you look very closely at the y-axis, it's upside down. So it's 35, 30, 25, 20, 15. So because it's upside down, everything's upside down and backwards. So this slope is actually negative. Yeah, so this slope is negative. And in fact, if you look at the rise or run, it rises from 30 to about 20. I'm just eyeballing. So it goes negative 10 in 65 to 2000. So that is negative 10 over 35. Any questions on that? Okay, and if you want, that's the same as negative 2/7. So we know the slope of the line is about negative 2/7. The y-intercept, by the way, is the y-intercept 30? What do you think? Okay, be very careful. Okay, notice that the y-intercept is when, by definition, is when x equals 0. And that the year 0 is not on this graph. Okay, it wouldn't even fit anywhere close to this computer page because the year 0 is way down. So the y-intercept's not very meaningful because one thing is Lake Clarity, in the year 0. Do you know how many people lived in Lake Tahoe in the year 0? Any guess? Yeah, 0. 0. We're way too cold and snowy. There's no food up here. You'd die if you lived here in the winter. So there were 0 people living in Tahoe in the year 0. There were people that would come for the summer, Native Americans, but definitely not all year round. So there are no people. It doesn't even make sense to talk about the y-intercept here. On the other hand, sometimes it does. Okay, in some cases for regression analysis, 0 matters, but in this case, it doesn't have any meaning. Okay. Also, when zero is very far from the data points, when there's no data points anywhere near 0, then it has no special meaning. On the other hand, what we can look at is this negative 2/7, which is about negative 0.28 or so. Okay, which tells you that the slope is negative about 0.28, and that is a rise over the run. So negative 0.28, maybe I'll just put it in here, negative 0.28. Oh, I'm on lines. That's what won't let me. Just a minute. Let's go back to Scribble. I think it'll work. 0.28. Sorry if it doesn't look good, but the annotation's not so good. I'm going to put it over 1 so we can think of it as a rise or a run. So the rise is a change in meters and the run is a change in time. So what that tells you that on average, there tends to be about a 0.28 drop in lake clarity for every year. Is that a good thing, by the way? Those of you who live in Lake Tahoe, you should know whether that's good or bad. Yeah, that's really bad. That's really bad. Okay. And in fact, given that it was, around 20 in the year 2000, if you multiply that by 20 years, because we're in 2020 now, then we got some serious amount of drop. And these are meters, by the way, that we're reading. So we're talking about 20 times 0.28, which is what, 5.6 meters. So that means we're having a drop in lake clarity of 5.6 meters. We're talking about, close to 20 feet. Okay, maybe 17 feet. And that'd be awful. Okay, that'd be awful. Okay, our lake would start looking mossy and terrible. Any questions on this so far? Any questions? Okay, so here's the good news. The good news is President Clinton at the time understood science. Okay, and my feeling is we should always have a president that understands science and trusts scientists. Okay, whoever that might be, but I think it's a good thing to have because, well, I'm a professor, so obviously I support science. Okay, so understood statistics, understood science, listened to the UC Davis professors and scientists, and realized that if we didn't do anything, that this regression line is going to help predict what's going to happen in our future, and the future will be no clear lake blue Tahoe anymore, just murky, ugly Tahoe. Okay, so do you know what happened? Anyone know the history? Okay, and not only was Clinton there, actually, I believe, I forget what senator, but there were a couple senators there too. Okay, so if you don't know what happened, let me tell you. What happened is that they went home to Washington, D.C., and they passed a law that said that they're going to fund the Lake Tahoe Clarity people, basically, a huge amount of money. We're talking like over $100 million to fix this problem. So that's the history. Had statistics not been there, we'd probably have a murky lake right now because they wouldn't even bothered. Yeah, so now let's take a look. So can we save the lake clarity? Well, let's look at what happened. Now let's just glance post the year 2000. Take a look at that data. What do you notice about lake clarity after around the year 2000 or so? Is it still doing this whole linear thing? If it was, we'd be over here somewhere. Lake clarity, it's not going up actually, and it's not going down, but it stopped getting worse. Do you see that? It stopped getting worse. Okay. And just to note, and again, you can run statistics on this, and this is important, and we're going to talk about that in a second. If you look at the years like 2011 and 12 and 13 and 14, 15, what do you notice about lake clarity? Yeah, it's gotten a lot better. Okay, but that's not necessarily because of good management, because after that it got a lot worse. Okay, yeah. Actually, it's the exact opposite, Michael. That was drought years. So I'm not sure how long you've been here, but those are the years of the drought. We had a severe drought, and if you have drought, you have really good lake clarity, it turns out. And then if you have a lot of weather, serious amounts of snow, then you get terrible lake clarity. But if you have people and no controls, then it goes up and down, but slowly keeps going up. Do you see the difference? So I want to mention something. There's something, yeah. So it's flattening, but it's never perfectly flattening because weather goes up and down. That's weather has a high standard deviation. And by the way, just to let you know, it's off topic, but it's not. It's definitely important for stats. Is that, do you notice that the standard deviation has gone up? If you notice that, the ups and downs are a lot more. I don't know if you can see that, but there's a lot of fluctuation in the last 10 years or so. And there's a reason for that. Anyone know the reason for that? And that's man caused too, but not the same as the man caused, that the human caused issue that made this lake clarity just get worse and worse and worse. Do you know what the cause of the higher standard deviation is of the lake clarity? And in particular, the weather. Issue of shrimp? No, it's definitely not the shrimp. Okay, the reason is global warming, is climate change. And they have predicted, and we're seeing it, that climate change is going to cause a higher standard deviation in precipitation amounts. And when you have a higher standard deviation of precipitation amounts, you have a higher standard deviation of lake clarity. Okay, so I thought I'd give you something that's this is like the most applicable week there is. Does it feel like it? Okay, I just talked about two main things, at least in Tahoe and the world. One is the fact that if we didn't do anything, our Lake Tahoe would get horrible. And the second is that we see this high standard deviation, and that is actually climate change. Okay, and they've done lots of research, and the p-value is outstandingly small, which means that it's happening. Okay, climate change is happening, and the predictions are happening of a higher standard deviation of precipitation. Okay, any questions on that? Okay, I'm not sure. For me, this is like the most exciting thing there is in statistics. I hope I'm not boring you, because I think it's exciting that we can actually learn from statistics about what's happening on Earth. Okay, but again, I'm a science nerd, but maybe you like the stuff too. Okay, any questions on this? So one of the things you'll notice is that from the year 65 to the year 2000, this line is a nice fit. We got a negatively sloped line, and it looks positive slope, but it's negatively sloped line, but it's a nice fit. There's a number that talks about that fit and whether it's positively sloped or negatively sloped. And that number is called R. Okay, and R stands for the word regression. And but you don't call it regression, you call it correlation. So don't get mad at me for using R instead of C. That's what everyone in the world uses, so I'm using what everyone uses. So R stands for regression, but we call it correlation, even though it doesn't start with a C. Okay, and you'll notice that there's a pretty good what we call correlation in this time from 65 to 2000. Okay, and in fact, it's a negative correlation. Remember, it's a negative sloped line. On the other hand, from the year 2000 to today, there's no correlation at all. We don't have a positively sloped line. We don't have a negatively sloped line. It just goes up and down. Does that make sense? It's just all over the place. There's no prediction. You can't look at the year and having a good idea of what the clarity is going to be in between 2000 and 2020. But if you go between 1965 and 2000, then going on this line gives you a pretty good predictor of these points. Any questions on that? So I'm talking a lot. I'm not writing too much. We'll do some writing in a little bit, but I want to kind of go through something, to me, the most important thing there is in our town, and that's this. So then also, it turns out that a lot of times you want it to be positive, and R is negative if the slope is negative, R is positive if the slope is positive. So how do you, if you want to take numbers and want to ensure they're always positive, what can you do to the numbers mathematically? If you want to do something to all the numbers mathematically, there's really two choices if you want to make them all positive. Yeah, one of the choices is squaring, and that's what we're going to do. The other is absolute value, and it turns out mathematically it's evil, and I'm not doing it. So, and the world doesn't, because it's just math, does math issues. But squaring is nice. So instead of R, a lot of people look at R squared. Okay, so R squared, one of the things it does is it makes the correlation positive, or at least it makes the R squared positive. It takes the correlation and turns it into a positive number. And it also gives it some special meaning. So let me tell you about the meaning. Okay, so R squared from the year 1965 to 2000 is probably around, it's around 0.8. So I want to mention R squared is always between 0 and 1. The closer it is to 1, the tighter the fit of the line is. the closer it is to 0, the worse the fit of the line is. And the line might just be horizontal, and that's a 0 also. Okay, but in words, let me explain how you can talk about this. So we can say that at least between 1965 and 2000, one of the things that made the lake clarity change was the fact that people were coming in. Yep, R squared is always between 0 and 1, can never be bigger than 1, can never be less than 0. And in fact, if R squared is 1, then all the points are on the line. So clearly R squared is not 1 here, because there's no way you're going to draw a line that hits every point. You can't do that. Okay. And if R squared equals 0, it usually looks like the night sky. So the letter R is the first letter of the word regression. But unfortunately, it stands for correlation. Sorry about that. Don't get mad at me. Never shoot the messenger. Okay. But R squared is even more important. So again, as I mentioned, one of the things in between year 65 and the year 2000 is that there's more and more people that are, and as the population increased and there's more cars at Lake Tahoe and other things like that, then the lake's gone bad. All right. Well, if R squared is say 0.8, then I like to turn that into a percent. So 0.8 is what percent? Yeah, 80%. So what we can look at is we can say these points have a lot of variation, right? They have a standard deviation. And if you just looked at the y coordinates of all the points, there's going to be a pretty big standard deviation for all these points. Okay, because it ranges from around 20 to 32 or so. Pretty big range, big standard deviation. But if you just look at clusters around like a certain year, and you look at the standard deviation of each of the clusters, then on average, that standard deviation is going to be reduced by 80%. So a smaller standard deviation means you have a better predictor. Remember that? We've talked about that a lot with hypothesis testing. So you have a better predictor with a smaller standard deviation. Any questions on that idea? So we could say that 80% of that kind of variation, fluctuation in meters of clarity, is due to more people coming per year, basically, because that's what's going on. But then 20% is due to other things. The other things are things like weather, and that's going to change things. Weather's the major one, by the way. There's a few other things, but weather's the biggie. So that's what you can say when it comes to R squared, is you can interpret it as it gives you the reduction in the variation and how much of the variation is attributable to the x coordinate and how much isn't would be 1 minus that. On the other hand, if you looked at R squared between 2000 and 2020, that's probably more like 0.1, almost nothing. So then only 10% of the variation is attributable to the more people and that kind of stuff, because we don't really have a big difference in the people per year. Okay, at least the people causing issues. There's something called best management practices, BMPs, that have happened since then. And that's made it so that more people does not mean more problems. And as the years go on, we do have more people. So if you live in Tahoe, it's been packed the last few years. But the lake clarity has not gone way, way down. Any questions on this idea? Okay, so I wanted to do a very realistic one. You know, the problem with the realistic one is I have to talk about it. I could actually do all the calculations, but it would take too long because we got, 60 or so or 55 different data values. And we don't have the time in the, hour and a half of lecture to put 65 data values into a calculator. So that's why I just kind of talked about it instead of did the math. All right, but that doesn't mean we're not going to do something. All right, so now it's time to do the following. Well, I'm going to actually do a regression analysis. And what I want to do, let's do how do I annotate? I know there's a way to get rid of this annotation because when I go to another screen, I still have all those dots. Sorry. Let me stop share and reshare if that works. There we go. Then I think the annotation's gone. Okay, so what I'm going to do is we're going to do a regression analysis. And we're going to do a few things. One, the first thing I want you to do is I want you to answer two questions. And they need to be quantitative. And you might think that one might be related to the other. Okay, so I want to ask you as a group, any interest, something you want to find out about each other, where it's two quantitative variables where there may be a relationship where if you know one is high, the others might be high also. Any thoughts? Anything you want to do that you're curious about each other? So you can type in the chat box, say it, whatever. Don't be shy. So again, so examples, this might be a boring example, might be something like, I don't know, how old you are and how many units you've had at college. Okay, may not be what you're interested in, but maybe something you're interested in. Because you think that the older you are, the more units you might have had. Okay, that there might be that relationship, and maybe not. Okay. All right, we can do how many dogs and cats. The problem with that is that we're not going to get a lot of different numbers. Most people can be 0, 1, and 2. Something that you think might be related. It might not be related, but if you were to guess, you think it's related. So as one is high, the other is high or low. Okay, I like age, number of jobs because we'll get bigger numbers. Okay, I saw shirts and pants. That was okay. Most people don't know how many shirts and pants they have. I have no idea. But age, I hope you know your age, number of jobs, and again, the rule of the class is that if you don't feel comfortable telling people, then make something up that's reasonable. Don't say you're 195 years old because that's not reasonable. Okay, definitely not -2 because you are alive. Okay, so just a note, what I want to do is I want to do a few things. One is we're gonna look at age versus number of jobs. And I'm gonna write jobs you've had in your lifetime. And I'm gonna write down, because we're used to this now, what have we been doing the last 3 weeks in this class? What have you been doing? Yeah, hypothesis testing. So there is a hypothesis test we're going to do, and the hypothesis test is for correlation. All right, so what I'm going to do is we need an H naught. Okay, now correlation, when I write R for correlation, that's a sample correlation. We're going to be using the Greek letter. Now, who knows the Greek letter for R? You're not required to know it now, but you are required to know it as soon as I type it. Anyone know it? Anyone speak Greek here? In my 27 years of teaching this class, I have never had anyone say yes. but one of these days. Okay. So we have H naught, and the Greek letter for R is this guy. It's not a P, by the way. And the way you pronounce it is rho, like row your boat, except it's RHO is how you spell it. So rho equals 0. And that's another way of saying the correlation is equal to 0. Then there's H1. And in our class, H1, H naught, and H1 are always going to be exactly the same, okay, as every other example. They're not the same as each other. But it's going to be rho is there it is, not equal to 0. And that's always going to be in our class the null and alternative hypotheses for the test for regression analysis. So H naught says that there's no correlation between age and the number of jobs you've had in your lifetime. And H1 is that there is a correlation. If it's not 0, there's a correlation between number of jobs and between age and number of jobs. Any questions on that? Okay, now that we have that, let us collect our data. So what number calculator do you think you're going to be using? And the hint is we're almost done with this class, but we're not done. That's a double hint. Yeah, 24. This is going to be 24. It's regression analysis. So here's the calculator. And the way I programmed it, this big white box is going to be the scatter plot. Then we're going to put the points in. So what I want you to do is I want you to answer the question and answer it with a parenthesis, a number, comma, a number, and the parenthesis, where the first number you put in is how old you are, and the second number you put in is how many jobs you've had in your lifetime. So, and by the way, I'm not going to, this goes on YouTube, but I'm not going to tell you who said what. So 50, comma 17, plot point. The next one, 51, comma 7. Plot point. The next one, 27, comma 4. Plot point. Okay, the next one, 25, comma 8. Plot point. The next one, 29, comma 10. Plot point. The next one, 21, comma 6. Plot point. Okay, I think that might be it. Okay, any questions so far? Okay, so now we have all the information, again, that I put into this calculator that you need. So hopefully you understand now that at least I talked about it. Hopefully you somewhat understand all this stuff. So let's go through the first piece, regression equation. Y equals 1.9818 plus 0.1976x. Okay, do you all understand what that is? Can you let me ask you, because again, it's a little algebra review. What is the slope of this line? It's not a trick question. If you remember your algebra even a little bit, you'll remember, you can tell me what the slope is. So what's the slope of the line? Yeah, 0.1976. Okay, and what's the y-intercept of this line? So what's the y-intercept? Yeah, 1.9818. Okay. All right, then let's look at the next thing that we got. We got R equals 0.57. Okay, notice R is positive. Unlike the evil people at UC Davis, I don't try and trick you with this line. You could tell it has a positive slope line. Okay, any questions on that? You can see the scatter plot, you can see the line. I do adjust the axes so that you can actually see everything in there. So you'll notice that the scale is different on the axes. This one goes to 48, this one goes to 16, but I don't go upside down or anything. Okay, r squared is 0.328 or so, about 0.33. Okay, notice I actually put in the hypothesis. So there it is, h naught, rho equals 0, ha, so I used a instead of 1, rho not equals 0. And then you've seen this t before. When have you seen the t before? What chapter? Yeah, chapter 10 and also chapter 9. Okay, it turns out, and again, this is way beyond anything I can really talk about in this class, that the mathematics of getting the test statistic is equivalent to when we did the hypothesis test for difference between means. Okay, there's equivalent mathematical theory involved, but no way can I explain it. Okay, but that's the t. It's about 1.4. Now the p-value is about 0.23. Any questions on that? Okay, let me start with the p-value, 0.23. So let's go back. So the p-value equals 0.23. I'll give you 2 decimals is enough. What does that tell us? Again, just because you haven't seen this chapter before doesn't mean you don't know what a p-value is about. What does it tell you when the p-value is 0.23? Yeah, it's not statistically significant. There's statistically insignificant evidence to make a conclusion about there being a correlation between age and number of jobs a person has had. Any questions on that? Okay. So normally when you get a p-value that's that low, that means we quit. Okay, the regression line is useless. You shouldn't use it to do any research. The slope is useless. The y-intercept is useless because the p-value is big, which means there's no help in having this. Any questions on that? Okay. On the other hand, what was our sample size? Let me pop this back in. This one, sorry. Yeah, sample size was 6. Now, what do you know about a sample size of 6? Yeah, it's not normal. And not only is not normal, but it's pretty useless. Okay, you should never, ever do anything statistically with a sample size of 6. You just don't do it. Okay, but given the fact that we don't have enough time to do sample sizes of, of over 30, for example, okay, and actually even need more than that because you actually need normality for every value of X. So you need very large sample sizes. We're going to pretend that we had a low p-value so I can talk about the interpretations of all the other things. Okay, so again, bear with me. We're going to pretend that the p-value is lower. So I'm going to write had it been lower. Had the p-value been lower, here is what we can say about the statistics. Okay, so what I want to do is I want to look at all the statistics that the calculator gave us, and let's interpret them. So I'm going to start with the point. I'm just going to say 0.2 because rounded to a couple decimal places, it's still 0.2. So that's the slope. So let me write down the slope is 0.2. Okay, now 0.2 is equal to 0.2 divided by 1. Okay, you may think that's silly. I mean, of course it is, but there's a reason I'm doing that. When you think of slope, what do you think of? 3 words that you learn in algebra. What 3 words do you think when you think of slope? Yeah, rise over run. So I'm going to write rise over run. Okay, but it's a rise in what? So the rise is a change in Y. And Y are the number of jobs. Okay, so that's a change in number of jobs. And I'm just going to comma instead of over because that's how we're really going to be looking at it. And then we're going to have the X change because that's the run. And that's change in years, in age. Okay, so I'm really glad you asked. So as the number of jobs increases, the age increases. And the answer is you don't say it that way because that sounds like it's always true. Okay, and actually it's backwards. One thing is you go the other way around. It's age is X and jobs is Y. And the way you use X and Y is X is called the independent variable, Y is called the dependent variable, which means Y is dependent on X. So it's we're looking at a prediction for Y given X. So we have to look at it in the other direction than what you talked about. But you also can't state it the way you stated it because it's too matter of fact. And that doesn't work with regression analysis. So here's how we state it. So first thing, the change in age, the denominator is a 1. So that means for every year a person ages, on average, the person tends to get about 0.2 more jobs. Okay, and if you want to make it sound, 0.2 more jobs sounds weird, so you can multiply by 5 if you want to make it 1 job. So in other words, on average, it takes, or for every 5 years, a person ages, they have had 1 additional, actually they tend to have had 1 additional, I got additional already, job. Any questions on that? Any questions? Should be they. Okay, I want to highlight something very important. Tend. Okay, it doesn't mean they do get 1 more job. There's just a tendency, a prediction is another word you can use. Never do cause and effect with regression analysis. Got it? Okay. Don't do cause and effect. And you always have to make sure that you add words like predicted to or tends to emphasize the fact that it's not this is making the other thing happen. Any questions on that? Okay, it's a mistake many people make. And it's a disastrous mistake if you do cause and effect based on regression analysis. Okay, any questions on that? Hey, even if it feels like it might be true, okay, it doesn't mean that statistics do not give you cause and effect. All right, let's do number 2. And that is the y-intercept is about 2. 1.9818 is around 2. What does that tell you? What does that tell us? How to interpret the y-intercept in the context of this study? See if you can jump in. I don't see y'all jumping in. All right, let's think about it for a bit. Baseline? Not quite. Okay, so the idea is it's worthless. It's worthless in terms of understanding people. Because the y, what's the x coordinate of the y-intercept? Is 0. What does x correspond to in this study? Age. Okay, it makes no sense to say that a 0-year-old has had 2 jobs. So the y-intercept is meaningless. Any questions on that? The fact that it's meaningless here. Can the y-intercept ever be meaningful with regression analysis? What do you think? Yeah, so let me give you some examples because I want to make sure you realize that it can happen. Let's suppose I did a regression analysis and I looked at the number of hours that students go to get tutoring help. And I call that X. And then I looked at the grade on the final exam. Okay, the percent. Would the y-intercept have meaning in that case? Let's say the y-intercept was 68. Yeah, then it would, because then you would say that on average, students who don't ever attend tutoring, and there are students who don't attend tutoring, average 68% on the final exam. And that's very meaningful. Any questions on that? So the y-intercept has meaning in some cases. In this case, it doesn't. The slope always is meaningful. Just a note. Okay, now let's look at the other things we've got. R squared is the next one, and I'm going to use 2 decimals. It's best to use 2 decimals. And that's 0.33. So R squared is 0.33. And let me give you the meaning of R squared, and that's the hardest one. I've talked about it with the late clarity thing, but now let's talk about it with age versus jobs. And that is the following. There is a large variation, okay, or standard deviation if you want to write that, in the number of jobs students have had in their lifetimes. But if we only look at a cohort, I want to stop for a second. Do you guys know what the word cohort means? It's not a math word. It's an English word, but I've learned that some people don't know that word. Who knows what the word cohort means? Maybe no one knows cohort. I don't know. Like I said, it's not math. This is English. Yeah, it's a group of people banded together or with something in common. So that's what we're looking at. The cohort of students who are all of the same age. Then this variation on average is decreased by 33%. So not that much. It wants an S. So I want to read this again because this is, again, the hardest. This is the hardest of all of the statistics to try to understand. And that's R squared. Okay, so R squared value closer to 1 would represent less variation. It's not that it represents less variation. It represents more, a larger decrease in the variation, a larger percent decrease in the variation if you only look at those who have the same X value. Okay, you can't say it in a short way. So that's a warning. Don't try to make it short. You can't do it. Okay. So it says that, yeah, there's a reduction in variation if you just look at a certain age, but not that much of a reduction. It's only 30%, 33% reduction. Whereas the rest of it, 67%, is attributable to other things. Okay, and that might be, I don't know, class or race or all kinds of different things that students might have, where they live, who knows? Any questions on that? Okay, so these are the biggies. Let me kind of read through this. So again, we have our regression equation. Let's do one more thing, because I could ask this on a test. So use the regression equation to make a prediction for the number of jobs that a 40-year-old student has had in their lifetime. Any questions on the question? Okay. So this is easy. What do we do? And let me come back here. It's a 40-year-old student we're talking about. So what do we do? The hint is it's easy, but you have to know what to do. How are we going to make a prediction for a 40-year-old student? Yeah, we have x equals 40, and you're just going to plug in 40 right there. So let's do, I wonder if it'll let me highlight. Yep. Let's see if I can do it. So we take the equation and we plug in 40. We go times 40. And I can pop that into a calculator. And we get about 10, I think. No, sorry. Let me check. I can't see it anymore. There we go. Yeah, about 10. Okay, rounded to the nearest whole number, we're talking 10. So that's 10. So does that mean that if we find a 40-year-old student, that student has had 10 jobs? Yeah, we can't say that. Don't do the if-then stuff. If-then never works with regression analysis. Here's what we can say, is that the best prediction for a student, a 40-year-old student, actually for the number of jobs that a 40-year-old student has had is 10 jobs. Okay, very important, the wording. Okay, I will take off lots of points if you say something like, oh, a 40-year-old will have 10 jobs. That's wrong. Okay, you have to talk about it as a prediction, because that's what the regression line does, is it predicts. It doesn't tell us that this is going to happen. It gives us a guess. Okay, by the way, is this a good guess? What do you think? So what do y'all think? Is it a good guess or is it a bad guess? All right, you want to change your minds? Take a look. The p-value is 0.23. Okay, so it's not a very good guess at all. Yeah, so the p-value is 0.23, and not only that, the correlation was 0.33, not a high correlation. So this is a bad guess. Okay, it doesn't mean there's a better guess that we can get, but it's not very helpful. Okay, the regression line is not very helpful when you have a p-value of 0.23 and an r-squared of 0.33. Just a couple things, some language. If r-squared is, come on, there we go, is greater than 0.8, then we say there is a strong correlation. Okay, and that's not a perfect number. So I've seen people use 0.7 also. 0.8 is a little more common, but I'm just telling you when we have a strong correlation. Okay, and if it is in between around 0.5 and 0.8, then there's a weak correlation. Okay, otherwise, there is little to no correlation. Okay, so those are the numbers I'll use for now. Again, it depends on the stats class you take. Some people use 0.7 instead of 0.8. But if it's like 0.95, we have a very strong correlation. If it's 0.2, there's really no correlation there that you can notice. Okay. If you looked at the scatter plot, you're not going to see a line. You're going to have to be very drunk to see a line. In other words, no. Or maybe stoned, I'm not sure. Okay, so that's kind of how some of the language we'll use is we'll say strong correlation, then we'll talk about weak correlation, little to no correlation. Those are the words you usually use when you're talking about correlation. Positive correlation, negative correlation. Oh, sorry, that was supposed to be R squared. Positive correlation, negative correlation. That's R being positive, R being negative. And the sign of R is always the same as the sign of the slope. So if R is positive, you have a positive slope line. If R is negative, you have a negative slope line. Any questions on those pieces? Any of you lost? Any questions? Because I talked a lot, but it's very important. It's used a lot. Any questions? This is one of the most useful topics of all of statistics. Okay. How do you use it to make money? Maybe none of you care. Product equals profit. Not sure exactly what that means, but maybe. So there's a few ways. One, if you have a business, and if you can find out that you have a correlation, say between the amount of money that you spend on advertisement and the number of customers that come into your store, and that correlation is strongly positive, then you're going to beef up your advertisement funds. On the other hand, if you find out there's no correlation between the amount of money you spend on advertisement and the amount of customers you have, don't spend money on advertisement. Okay, but you got to do the data analysis to see it. Okay, you need to have that data. Any questions on that idea? Okay, so whenever you're doing businesses, you want to look at correlations, and then you want to change your business practice based on that data analysis. Okay, any questions on that idea? So that's one big way of making money if you're a business person. And by the way, I'm not a business person. So I could tell you the statistics, but I don't have the experience in doing business. I just know the math. Okay, I'm a teacher. And one of the nice things about our job is we don't have to worry about that. Okay. Any questions on that idea? It's always good to know how you make money on stuff. All right, let me, so I don't forget, because last time I did, show you the secret word. And the secret word for this week, week 10, is prediction. Because when you're looking at a regression line, then we're talking about getting a prediction for Y knowing X. So prediction is a very important word in regression analysis. Sometimes you use variations of it like predicts that. Our best prediction is. Any questions on that? Okay. 7:24. I always try and end between an hour and a half, usually on the hour and a half side, but try not to go over an hour and a half. Just want to let you know today, this is our last regular webinar of the quarter. There's still one more webinar, not next week, but the week after. And what's the next webinar going to be about? Most of it? Yeah, the final. It's going to be a little of chapter 13, probably 20 minutes or so on chapter 13, and then all the rest to talk about studying for the final. and getting ready for it, practicing. So next week, there's nothing. Okay, there's nothing due next week. But if you're behind, you still might want to study a little bit. If you're not, take a break. Okay, your extra homework a week from Thursday, any guess? Is to gain weight, because that's how you be a good American. On Thanksgiving, you're supposed to eat a lot. So there's your extra homework next Thursday. Some of you might be working. I won't be working. I'll be eating turkey. Okay, so I'm going to stop the share. And then stop the recording.